Hello, brave few, back for more punishment. So my talk today, entitled Programmer, Program, Machine and Environment. My name's Andrew Sorensen. I'm from Queensland University of Technology, which is in Brisbane, Australia, so it's sort of about halfway up the east coast. And I guess another name for my talk could easily have been Live Coding the World. And by this, what I mean is that I'm really quite interested in the context of live coding real-time systems. And by live coding real-time systems, I mean real-time systems that are connected to the built environment in some meaningful way. So I'm not talking I'm not talking about just real-time sort of live programming of some real-time system that's running underneath. I'm talking about real-time, so actually live coding the real-time system itself. The main context for my talk, although certainly not the only context for this area, is audio-digital signal processing. And for any of you who've sort of worked with audio before, it's a pretty nasty, demanding mistress. So, for example, my little audio device up here is running at 192K, which basically means there's 192,000 samples being demanded by the audio device every second, and that's times 2 channels. And that, if you want to do a sine wave, then that's 192,000 times 2 just for one sine wave, but of course we want to run hundreds of sine waves and all of these other things at once. So you have very, very small, low latency, but still high compute. So it's actually quite a challenging real-time domain, still remains quite a challenging real-time domain. But I guess I could also have kind of called my talk Live Coding in the World, because one of the take-homes that I'd really like you to get out of today is that programming doesn't have to be about a product. It doesn't have to be a destination. Programming can also be about the journey. Hopefully some of you were at the performance earlier, and you would have seen this idea that there is no kind of finished product to that performance, right? The performance is the journey. The programming actually makes up this journey over time. And so there's this kind of idea of steering an algorithm through time, where we're manipulating the algorithm in real time, and that algorithm is then having some effect in the physical world. But this also means that programming is sort of situated, right? So I'm situated in the world while that activity is happening. So the program's generating sound, which is going out through these actuators, these speakers that we have down here, which is perturbing the environment. So we have these sound waves bouncing out into the acoustic space in here. And I'm listening to those sound waves, and I'm changing the program in response to what's happening in the room. And then, so there's this sort of cyber-physical coupling between me and the program and the machine and the environment, and they're all sort of working together. So I'm sort of just reiterating a couple of slides you've already seen. So this is really just for those who weren't at the keynote. This kind of live coding of musical performances is something that I've been involved in quite heavily for the last 10 years. And the idea of this activity basically is that we're writing a program, often from scratch, but it doesn't have to be. My particular style is to sort of start from scratch, so you have a blank text editor, and the program sort of slowly evolves, and people can kind of watch this code sort of build. And hopefully then they're able to kind of connect with the code in a more meaningful way, because they can see it all sort of start to grow and expand. And it's important to note that this isn't just necessarily for literate. This is sort of for illiterate. I don't mean that in a negative way, but non-programmers, for example. I think this is still really useful for them to see that there is some kind of activity going on, and they can see it sort of growing and changing and expanding. And whether or not they understand the code doesn't necessarily detract from their experience of this thing, this sort of living text that they're watching. As I mentioned earlier, these kind of performances have happened in all kinds of venues, both very small venues and very large venues, in front of small audiences and large audiences, and they're not necessarily electronic. So, as I mentioned earlier, this is me programming a couple of robotic pianos. So this is a purely acoustic performance that people are listening to. There's no electronic music. Well, there's no speakers involved in this performance. There's generative music being created by the computer, but it's an acoustic jazz performance being played by the robot pianos. And as I was saying earlier, certainly the bread and butter is electronica still, and so this idea of sort of live club performances as well as more experimental electronic scenes. But as I was saying before, one of the things that ties all of these things together is this idea of sort of guiding algorithms through time, and the fact that we can change and morph code while it's executing, and that this kind of real-time behavior has some interesting properties, which we're about to get into. So it's probably worth starting with the question, I'm talking about live coding, and it's worth asking the question, what does liveness really mean in the context of live coding? I mean, what is this liveness that I'm speaking about? I mean, we've certainly had kind of this interactivity, this dialogue with the machine going back to the REPLs of, the 1970s. And so it's interesting to ask the question, what is it that we're talking about that extends from this? I mean, I can ask a question of the REPL, and it can give me a response. I can enter values into the REPL, so I can say something like, this, and then I can ask a question of the REPL. I can say, what is the result of amplifying coffee with chocolate, right? And, of course, there's only one possible answer to that question. Thank you very much. We can define functions, right? So, on the fly here, I can say, my square, and then we can call my square. It's all very exciting, right? So we've seen this, ad infinitum, right? So there's nothing new going on here. It's also worth thinking that, there's quite a strong similarity between the Unix shell and the REPL, right? Where in a Unix shell, you're using a textual interface to interact with a sort of an underlying real-time system, which is the operating system, right? So we can do similar things in the REPL. So I can sort of say, what's my current working directory? Or I can ask, what's the contents of the current working directory? So all of this sort of interactiveness has been in the REPL for years. So what is it that I mean that's different about live? And we're going to start getting into this now. So let's have a look at a fold function, okay? So what this is going to do is it's going to fold over the first 100 integers. It's going to reduce the first 100 integers, basically. And we get the result, 5,050, okay? If I use a minus here in the fold, it's going to give negative 5,050. Just keep that in mind. Negative 5,050, 5,050. Okay. So I'm going to jump up the top, and I'm actually just going to pull up a definition of fold. And I'm going to put a print line in here so that we can have a look, sort of inspect the value of a cum as it's going around this fold function. So now let me just start this off. Okay, and now we've just dumped out basically a cum each time round. And we've got the same result for plus. It's given us 5,050. You just have to trust me, minus would do the same. Okay. Now what I want to do is I'm going to slow this down a little bit. So I'm going to put a sleep in here. So this time round, we're now going to see this accumulated value. And we're seeing it's just sort of accumulating up or reducing down, whichever way you want to think about it, until we get to the final result. Now, where I think this liveness question comes in is now, okay? So this time what I'm going to do is I'm going to run this function again, but I'm actually going to jump into the function and change its definition on the fly. And when I evaluate this, it'll double flash, and all of a sudden you'll see the accumulated value going down, right? Now, if you think about it, this is actually a bit scary, right? Because all of a sudden we've lost referential transparency. We've actually got this divergence between what's happening in the text and what's happening in the executing process. Because what does the answer minus 1,268 mean, right? It's sort of anywhere between minus 5,050 and positive 5,050. And the thing that makes this even maybe slightly more concerning is that the when of when I do this really matters, right? So if I run this program again, I'm going to set it back to what it was. So remember that, minus 1,268. And I run this program again. La-di-da-di-da. We fold again. Minus 1744, right? So all of a sudden, the result that this program is going to give is absolutely integrally related to my changing of the function in time. So let's make this example a bit more obvious, okay? So this steering of this algorithm through time. So if we change the print of the accum here to a note, okay? And I'm going to just take the accumulated value and use it as a frequency. And hopefully this won't be too loud. Just block your ears, everyone. I'll just change this back to funk again. Okay, so what I'm about to do is we're just going to sonify this fold function. Okay, so let me evaluate this. We'll set it off. Okay, everyone hear that all right? Beautiful, right? Lovely melody. I'm sure you all very much enjoyed it. My job here is done. So now, this time around, I'm going to do exactly the same thing, but I'm going to play this melody, right? So, play. Anyway, here we go. So there's this interesting property now that the observed state of the program, effectively the value of this accum, actually becomes very important to what I'm doing, right? Because this accumulated value is the pitch that I'm listening to, and I'm changing it as I go through. So, in effect, what I'm trying to explain is that while we're losing some nice properties, like in theory, this should be a pure functional with referential transparency. The function should tell us the result by its definition. This ability to guide and steer these computations through time can be very useful. So I think it's a property not always worth giving up, of course, but sometimes it is worth giving up, and that there are some useful benefits of doing this. So a fold function probably isn't a particularly good example of this for obvious reasons. Let me give you a different context now. This is some work I'm doing with some colleagues at the ANU, the Australian National University, Ben Swift and Henry Gardner. And this is looking at using live coding for plasma physicists. So what I'm going to do is I'm going to run a particle simulation, a particle in cell, PIC simulation. So this is a physics simulation, basically looking at fields, particles and fields. I'm not a plasma physicist. I'm not even going to try and explain what it's doing. I'm working with plasma physicists to do this work. And I'm going to start it up for you now, and then we're going to have a bit of fun diving down into the low-level code and changing that so that we can see some effects with the simulation in real time. One of the points that I'm trying to get across with this example is it's actually quite a high-performance example. There are hundreds of thousands of particles running in this example, and it's doing a lot of compute work to calculate the fields and the velocities of all the particles. So let me just start this up here, and I'll turn that down. Can everyone see that? Sort of. So we've got some particles, and they're all kind of floating around there in space. And we can do some, high-level things to this particle system. So I could do some things like, say, we'll double the speed of the step. So this is basically just the simulation rate that we're looking at here. I could double it again, but we'll just set it back to 1. But we don't really want just this high-level interaction. What we really want is a lower-level interaction, being able to dive down into the code. So I'm going to show you an example of that now. So here we've actually got the PIC code. And down here, let me just change this out, because this is what I'm going to show you guys. Da-da-da-da. Okay, so in this post at the moment, it's basically passing in -1, which is an electron for all of these particles that are going around. And when I can connect this up and I can compile it on the fly. And what I want to do is I want to shift this so that rather than passing -1 round as the charge, I'm actually going to pass around this cosine. and it's going to be shifting the charge from a negative charge just slightly into a positive charge and back, and it's going to oscillate between these two values. As it does, it's actually going to build up energy in the system, so I'm then going to have to turn it off again, but we'll just build up a little bit of energy and we'll see what happens. The cool thing is, because I'm not a plasma physicist, I don't actually care what this does. I'm just trying to make some pretty pictures, right? So let's just see what happens when I compile this in here. Okay, so we're starting to see these kind of cool resonances build up in the particle system here. And this is, again, this is me changing this this is low-level code. This is basically for every particle in the system that it's going around here. I'll just push it in again. So we'll compile the change in again. And again, you'll see it, the resonances kind of building. Okay, so we've got this ability then to go in and steer this algorithm, and we can actually view the results of this while we're doing it, which is hopefully something that's going to be useful for people like plasma physicists when they're exploring these computational systems in real time. And it's worth thinking about again, and what I'm trying to get at here is that this observable state matters, right? So when a physicist is looking at this information, we're hoping that they'll see interesting patterns that actually guide their exploration of the space. So this is sort of ephemeral programming, right? It's programming as an exploratory practice, an experimental and exploratory practice. So let me also just change, and what I'm going to do now is I'm going to completely ignore, I'm just going to throw in completely random positive charges here. And we should see all of the particles start to attract. So this is just throwing in completely random positive charges. I'll compile this code in now. Right, and so we see this kind of nice patterning happening where all of these charges are now pulling each other together in interesting ways. But again, as I said before, I have no idea what I'm doing. I'm just making pretty pictures. But we're hoping that this kind of stuff proves to be useful to people working in the space. Okay, let me just stop this simulation now. Oops. Just hide this for a sec. So what I'd like to do now is, first of all, let me jump back to the slides. Oh no, broken it all. Bump, ba-dum, bump. Skip. Okay, let me quickly talk about Extemporary. So the musical performance you heard earlier today was all written in a programming language called Extemporary, which I'm sure most of you noticed was very Lispy looking in the sense that it's an S expression language. It's a strict call-by-value language. Obviously, S expression, it supports, many bits of sort of traditional Lisp goodness, lexical closures, Lisp macros, and it has a very sort of scheme-like block structure and style. But actually, in most ways, Extemporary is not very much like a Lisp. It's actually completely statically typed. It's a type inferencing language. It supports expressive data representation, by which I mean it supports things like architecture width primitives. So things like SIMD registers are primitives in Extemporary. It has supported memory management, not garbage-collected memory management. One of the things that we're really interested with all this real-time stuff is that we actually want very deterministic behavior in both time and space. It supports generics, but specifically specialized generics. There's no boxing going on. Again, this is for performance reasons when we're working with real-time systems. So Extemporary is designed to be fast, but more than being fast, it's designed to be determinate. And this idea of determinism basically being that we have some good idea about exactly what our performance profile is going to be for this code as it executes. So I'm going to jump back to the code here again. And now we're going to have a bit of a look at this in the context of the performance I did. And I'm going to step through a little bit about how this actually works behind the scenes. And there's two things in particular that I'd like to take a look at. The first one is the timing that happens in this sort of higher level music structure and how the scheduling of all of that stuff works. But then after that, we're going to sort of dive into the audio signal processing, and we're going to start working our way down through, from an instrument through to sort of unit generators, into the unit generators, and then right down to the audio device. And we'll just sort of see how Extemporary allows us to, on the fly, hot swap this code all the way through. So let me, I think I've still got the code from the performance down here. But before I do that, let me just start with the simplest kind of temporal pattern in Extemporary is that we can perform an event. We can say an event, we want a particular event to happen at a particular time. So what I'm going to do is I'm going to evaluate this now, and we should hear this note sound. Okay? So I evaluate the expression, we hear the note sound. I could make this random, right? I could say each time I evaluate this expression, I'd like it to produce a different note. Okay, so each time I evaluate, it's going to choose a new random pitch to play, but all these are happening, now, immediately, whatever now means. We'll kind of get into that. I can play multiple of these at the same time. We can have simultaneous events, effectively. So here I'm going to just play 5 at once. They're completely random pitches, so it's going to come at you as a bit of a cluster. Right? But we can also start to think about scheduling these things into the future. So what I'm going to do is I'm going to increment now. I'm going to say, I don't want now, I want now into the future, sometime into the future. So let's say 1/10 of a second again. Whoops. And now what it's going to do is the same as before. It's going to play a cluster, but it's not going to play them together. It's going to space them out. Okay? Of course, we can play lots of these things. Okay, so we have this ability then to precisely schedule when things happen. Extemporary has a real-time scheduling engine built in. But this idea of scheduling things like notes is actually just built up on a more fundamental abstraction, which is the idea of being able to schedule functions at very precise times. So I can do a similar thing here by calling schedule, and I can say I want to schedule now the anonymous function that takes no arguments and prints, hello OSCON. Okay, we'll schedule this, and in my log you've just seen it's just printed hello OSCON. It's just printed immediately, so I evaluate again and it prints it immediately. But of course we can schedule this anonymous function into the future, right? So I'm going to schedule this function call 1 second into the future. Okay, so we get OSCON printed into the future. Of course, we can start to nest these things. So I can say I want to play a note now, again, on my FM synth. But I'm actually going to play the note, well, no, I'll play it now. So we should see the note and the text appear at the same time. Okay, so in 1 second, we get both of those printed. I could push this note 1 second into the future as well. Okay, so we get the hello printed after 1 second, and then the note happens after a following second. So we get it 2 seconds later. But really what we want to be able to do is, rather than using an anonymous function, it's kind of neat if we name our function. Okay, so what I'm going to do is I'm going to say, define my new f, and I'm going to pass in a pitch as an argument, and then I'm going to use that pitch value over here. And then down here, what we're going to do is we're going to use this schedule. Let me pull this down here. We're going to change this back just to be now. And we're going to call back to this my new f. Okay? And we have to pass pitch round, of course, because it's going to expect an argument. Now down here, I can start this off, and I'm going to pass in a pitch value of 60. So let me now start this up. Okay, so now we have this interesting effect where we're playing, my new f is being called, it's playing a note straight away, and then it's scheduling itself for some future invocation or execution. Okay, it's passing around an argument, but it has two kind of nice properties about it. One nice property about it is that it allows us to change things. So for example, if I want this to run faster, I can just change this code. I don't start a new temporal recursion. I just recompile this on the fly. And it's going to pick up on that new change and start using that new value. Another nice property of this is that this has a nice property of being asynchronous. So we can establish concurrency by using an asynchronous cooperative concurrency model, which means I can start multiple of these things at the same time. So let me start one with a different pitch. Okay, so now we've got 4 of these things all running at the same time. And we can actually interact with them quite directly as a group. So for example, I could change the pitch each time around here. Okay, so we have these 2 nice sort of abilities out of this one concept. The ability to change things on the fly and the ability to run multiple things at once, so multiple concurrent events at once. Extemporary supports not just cooperative concurrency, it also has process concurrency for doing multi-core stuff. So for example, the physics simulation stuff you saw before. And we'll also see that things like compilation aren't affecting what's going on. We're able to compile code and do all of these things while everything's running without unduly affecting its real-time processing. But at this stage, what I want to do is I'm just going to stop this. It's worth pointing out, how do we stop this, right? So the way we stop this is, well, there's 2 ways. There's the nice way and there's the dirty hack way. So I'll show you the nice way first. We say if false, right? Because next time round it goes no callback, so there's no future occurrence. The dirty hack way is actually just to define the function as nothing, and then it actually just bombs out with an error. But it's really quick, and it works well when you're doing live performances. So what I'd like to do now is I'm actually just going to go back to some of the code I had for the performance earlier. Let me just start this up again. And I want to start digging down into the audio signal processing that's going on behind the scenes here. So let me get this started. That's interesting. What's going on there? Let's do this. Oh, I know what's going on. We need some volume. Okay, so what I'm going to do now is I'm going to jump down into the FM synth code and we'll start modifying it and changing its behavior. So let me just jump over here. I'm going to go into the library code for this instrument. And somewhere in here we have FM synth. Okay. So this is actually now, this is a higher order function, so it's a function that returns a function. The reason we use that is that this gets called for each note that needs to be produced. And so each of those higher level functions then becomes a note so that we can have polyphony. We have multiple notes all sounding at the same time. And I'm going to introduce a new oscillator in here, OS3. And then down in frequency here, we're going to use OS3. I'm going to give it a frequency, an amplitude of 50. So it's going to move 50 hertz either side of the fundamental frequency, or the sort of the pitch of the note that's coming in. And we'll give that a rate of, let's say, 1 hertz. We'll compile this change in. Can you hear it's starting to warble a little bit? We'll change it again. I'll make it a bit more obvious. Okay, it's a little faster now. You can hear this effect. So basically what we're doing is we're changing this function, and this is an example of a function that's being called, 192,000 times a second, times as many channels as you've got, times n number of notes that are playing at the same time. So we can start to see that there's quite a bit of compute going on in the background here. As well as this idea of sort of higher order functions, we can also change the effect of the instrument. So we could change things like I could force a cutoff filter to 1,000 hertz here, and I could compile this in, and we'll see this will kind of bring the floor or the ceiling of this down. Okay, so we've heard it's now come down, and we've lost all of those sort of higher frequencies. I'll just push it back in again. Okay, but again, we've got this idea that this very low-level code is being compiled and everything continues to run and behave properly. We're not getting glitching in the system or anything like that. But of course, sort of introducing oscillators like this seems like a bit of a cheat as well, right? So we want to go, yeah, sure, but you've got an oscillator written in C somewhere, right? Well, no, we do all the turtles all the way down. So we're going to jump across to the Audio DSP library now, and we've got our little oscillator over here. So again, this is a higher order function, so an oscillator captures its phase. But what we can do is I'm just going to double the oscillator rate here. And we should hear every oscillator in the system just double in pitch automatically, because it's going to affect everything, which of course may not be exactly what you want, but it sort of gives an idea that all of these things all the way down work in this way. Oops, just connected up. Okay, so all the oscillators that are running everywhere have all just doubled in frequency. Take it back down. Okay, but you know, this isn't quite good enough either, right? There's definitely something else going on behind the scenes here. So what I'm going to do now is we'll go. Okay, so we have a DSP callback function here, okay, which is actually where this synthesizer is running. Now let me just do something really simple like this, just to give you an example. I'll just have to turn this instrument off for a second. Let me just turn this off. And I'm going to introduce white noise just to show you that this is actually what's going on. So I compile this in. Okay, so this is actually working now at the driver level. This is basically, all this function is doing is it's being called every single tick, and we're filling the audio buffer at the moment just with random numbers. So this is just white noise that we're listening to. And of course we can, you know, change the amplitude, the gain of this white noise just by multiplying it, right? So there's nothing sort of weird happening. This is literally just multiplying what's coming out of random, and we're changing the gain of this white noise. Just to give another example, we could do something. No, that'll do. We're bored of that. Let's get rid of that. I'm just going to put this back to the code that it was. But what I might do is actually leave the white noise in. So let me just leave the. Whoops, don't want to do that there. I'll do that here. We're just going to leave the white noise in. Oh no, what have I done? The white noise in. Okay. And I'm going to put the synth back in now. And we can see these higher order functions, this FM synth. This FM synth here is, again, it's also just producing samples on a per tick basis, but it's getting that information out of all of these higher order functions for all of these notes that are being played. So when I start up this right hand again, okay, we've now got this white noise also along with the synth that's playing along behind it. So all of this kind of activity is all compilable right down to the lowest levels of the DSP code that we're running, which is the point that I'm really trying to make here. So I've kind of given some audio examples today, but I kind of want to also then give you an example of where this has been applied in a bigger project. So let me stop this, and we'll also make this silent. And let me just come back to my slides for a second. Grr. Okay, so I'm very lucky that at the university I work at, we have a brand new science and technology centre. And one of the things that got built into the foyer or sort of lobby area of that new centre is this huge new interactive touch display. So the bottom panels that you're looking at all along the bottom there are all 55-inch multi-touch display panels. Effectively, they take any number of touches. Each touch is at about 100 hertz. There's also then a top strip along the top, which is edge-blended projectors. So the bottom strip is all interactive, the top strip is all fixed. But all of this scene is running in high def, so each one of these 55-inch panels is running high def. So if we actually want to be able to render on this at full definition, we're actually rendering on 8 different compute nodes. So this is a distributed problem. We're drawing this one big scene, but we need to coordinate all this activity between all the nodes that are running. And this is me, a picture of me live coding this wall. So the cool thing is that I can work on this while people are interacting with the wall and change all the physics code, all the display code, all the rendering code, all the audio code that's happening while they're playing with it, and it's happening in a distributed context. So I just want to play you a quick video just to give you an idea of how this wall works in practice. Things like all the classical mechanics, obviously, for controlling all the block positions and all their interactions also has to be distributed across all of the nodes. Even things like the water here, right? It's still, you're seeing it splash across multiple screens, and so all of this stuff has to be distributed across all the things in the context. Again, the same for sort of fluid simulation code, playing with sort of famous science heads. And this is really designed for sort of lower high school, upper primary school kids. You might have seen black panels come up before where it's got sort of the basic maths of all the things that are going on in the simulation. We're trying to kind of get them excited about learning the maths because they're playing around with this fun thing. And then we go, and by the way, you should see how this kind of works behind the scenes. This is me pre-beard. Okay, but this is going to go on, and I'm running out of time. So I'm just about to get to thanks questions. Really, what I hope you got out of this is this idea that steering algorithms through time can be quite an interesting behavior. So even in the context of doing the playroom, the cool thing is the playroom was running in our lab while we were working on it. I'd come in the morning, the playroom's already up and running, I just connect to it and start sending code to it. People serendipitously kind of walk into the room and start fiddling with it, and I go, that's not working, and you just go in and change it while they're fiddling with it, and you can kind of see their interactions while they're working on it, and then the next day you come back, and the same, and it's kind of like there's this living, evolving system that you're just working with all the time. But I've run out of time, so thank you very much for coming along.